Okay, we're back. Here we have a check-in number 3 for AP Physics C. This one has to do with electric potential. So if you haven't already looked at these, take a look at these. The picture that I had sent to you looks something like this. Forgive me for these hand drawing, but you've got a set of equipotential lines starting at 0 volts, 5 volts, 10 volts, 15, 20, and 25 volts, and different points on the figure A, B, C, D, and E, and a bunch of questions that go along with it. First of which is at a higher potential, A or C? If you see the line for A is at 5 volts and that for C is 10 volts, we're going to say that the potential for C is greater than that of A, because C is at 10 volts, which is at a higher potential than that. You just read it right off the figure. So C is the answer to that. C is at the higher potential. Next question. What is the direction of the electric field at point C? Well, the electric field is defined to go from higher potential to lower potential. So I'm going to say that the electric field on this figure, if you look at it, is going to go from 10 volts to 5 volts. So the direction of the electric field there should be between C and up towards on that figure. It's got to be in that direction. Hopefully that makes some sense to you. Next one is, how much work is required to move a 20 millicoulomb charge from A to B? So you've got a charge that's given 20 millicoulombs, and how much work is required? Well, the work is going to be equal to the amount of charge times the potential difference. From A to B, though, you may think it's a trick question, but they're both at the same potential. So actually, the potential difference between A and B is 0. So if you multiply 0 times whatever that charge is, it's going to require you 0 joules of work to move that from A to B. And it says in the last question is repeat that's part B or part C, but if you're going to do it from A to E. So if you're going to move it from A to E, now you have a potential difference because the potential at A is 5 volts, the potential at E is 20 volts. So I think the charge times the potential difference, we would actually do a calculation. 20 millicoulombs is 20 times 10 to the negative 3 coulombs. And the difference in the potential is 15 volts. It goes from 20 to 5 to 20, so the difference is 15 volts. You're going against the field, so you're going to have to put work in to get a positive charge to go that. To get to the higher potential, you're going to have to put in an amount of work. If you do that, I think you do that calculation, you get 0.3 joules of work. Let me repeat that one more time. Since you're going from lower to higher potential, you're going against the electric field, you're going to have to put work in to get that positive charge to go from point A to point E. Okay. The next question has to do with parallel plates. You have this set of parallel plates. You have this figure, positives on one side, negatives on the other. Potential difference between those plates is 250 volts, and the distance between the plates is 15 centimeters. And you want to know what is the strength of the electric field between those plates. You have the equation that the electric field is equal to the potential difference divided by the distance, because V equals ED is the equation we sometimes use in class. So here I can just plug that in. I'm going to have 250 volts and divide by 0.15 meters, which is the potential, or is the distance between them. If I do that, I get 1667, and the units for electric field, one of them would be volts per meter. Just seems reasonable. The other set of units might be newtons per coulomb, but here volts per meter would be applicable. If you're worried about the electric field being non-uniform, that isn't the case here if you have a whole set of charge of positive on one side and negative on the other. When you do that integral of E dot dr, you find out that the electric field pulls out of it because it's constant. And as a result, you end up with this equation that's pretty straightforward. Let's say we took a proton, we released it from the positive plate. How fast would it be going by the time it reached the negative plate? It's a pretty straightforward problem, but something you see a lot in the AP Physics exam. I think I'm just going to use energy conservation, E equals E prime, for that, and say that the potential energy stored in the electric field is going to turn into the kinetic energy. So this would be Q delta V, like we had in the other problem, is equal to 1/2 mv squared. And so you would have to look up on your formula sheet what some of these data would be, but the velocity, if I move things around, I'm going to have 2q delta v over m, where the charge is that of a proton and the mass is also the proton. So let's just put in some numbers and see what we get. We got 2. The charge on a proton or an electron is the same, 1.6 times 10 to the negative 19th coulombs. The potential difference in this particular problem is 250 volts. And then divide by the mass of a proton, which is, you could look it up, 1.67 times 10 to the negative 27th kilograms. You can figure out the units just to make sure that it's meters per second. Look through what a volt is, a joule per coulomb. Your coulombs cancel. But if you do the math on that, I'm getting it, it's 2.19 times 10 to the 5th power meters per second would be the speed of that proton by the time it reaches the positive plate. Okay, so that's that part of the problem. The next part of the problem says, how about if we add a little bit to it and say, what if there's a dielectric material that has a dielectric constant of 2.5 and you place it between those plates? When you put a dielectric material in there, we've talked about this on one of the other videos, that does something to the electric field. So we'll take a look at how that works, but they want to know what is the new electric field between the plates. Well, if it's a parallel plate capacitor, we would say that the capacitance is epsilon naught A over D, and you'd multiply by that dielectric constant to get the new capacitance, because the capacitance of a capacitor that doesn't have a dielectric would just be epsilon naught A over D. The electric field is going to be reduced. You can do, probably it would be wise for you to look this up, but how it changes. But the electric field is reduced by that same dielectric constant. We talked about the fact that when you put the dielectric in there, it polarizes the material, and then the electric field is weaker just a tiny bit because it polarizes the molecules of that dielectric, and they set up tiny electric fields that are opposite to the direction of the electric field between the plates. So as a result, the electric field is dropped by that same amount. So the electric field is now what we got on the other problem, which was 1667 volts per meter, and then we're going to divide by 2.5. The dielectric constant has no units, but that would give you that the electric field would be 667 volts per meter. It has reduced by that amount, by that factor of 2.5. Now it says do that same calculation and find out what the new speed of the proton would be. Well, it's going to give you that same result, that you're going to have square root of 2q delta v over m to find it. And all you do differently is find out what the new potential difference is. If V equals ED, then we need to find out what the change. We're going to have to find a new potential difference, because the thing that changes, that doesn't change, is the distance, but if the electric field changes, so does the potential difference. So you're going to have 667 volts per meter, and you have your 0.15 meters again. So the new change in potential between the plates is now 100 volts. Instead of there being a 250 volt, that has also dropped by the same factor of 2.5. And so you can just plug in 1.6 times 10 to the negative 19th for the charge, 100 volts, and 1.67 times 10 to the negative 27th is the mass of a proton. And if you do that, I think it has reduced the velocity down to 1.38 times 10 to the 5th meters per second. So I would advise you to go through these calculations and see if you get the same answers that I do. I hope this was useful. We'll catch you for the next check-in soon. All right. Best of luck. Stay safe. Thank you.